Hello and welcome to a new module on derivatives. Today, we will explore examples of how to calculate a Taylor polynomial for a given function. The requirements are simply knowing the derivatives of elementary functions, such as quotients and the natural logarithm, and some basic mathematical operations. Let's compute the Taylor polynomial for the natural logarithm of x with the center at x equal to 1. We will also determine the error involved in approximating the value of the natural logarithm of 1.2. To begin with, we will calculate, even though it's not explicitly stated, up to the third order. Well, what do we need to do? The first step is to take the function and differentiate it n times, in this case, 3 times. The derivative of the natural logarithm of x, which I think is quite simple and you probably know, is 1 divided by x, and I'm expressing it as x raised to the power of minus 1 to make it easier for calculation. The negative exponent indicates that it's in the denominator. Conversely, if I have x raised to the power of 1 in the denominator, I can write it in the numerator with the same value but a negative exponent as shown on the screen. Moving on to the next derivative, the derivative of 1 divided by x is minus 1 divided by x squared. It's quite straightforward when you view it this way. When differentiating x raised to minus 1, the negative 1 moves to the front, you have the negative sign here, and when you subtract 1 from the exponent, you get minus 2, so you have the minus 2 here. The next derivative, the third one, is simply obtained by differentiating this quotient. You can do it using the quotient rule, or you can utilize the expression provided here. Using it makes it straightforward. The exponent, which is minus 2, comes down, multiplied by minus 1, which gives us 2. And I subtract 1 from the exponent. As it was minus 2 minus 1 is minus 3. And then I have the third derivative. Converting this expression into a fraction is quite easy. You merely place x raised to the minus 3 in the denominator. We already have the derivatives necessary for calculating the Taylor polynomial. What's the next step? We need to substitute the derivatives into these functions by replacing x with the value we were given at the beginning, which is 1. Why use 1? Because it's straightforward to calculate. The natural logarithm of 1 is simple, and we'll see that shortly. What's the value of the function at x equal to 1? It would be the natural logarithm of 1, which equals 0. This is a well-known value that you should be familiar with since it frequently appears. Next, how much is the first derivative at x equal to 1 worth? The first derivative is 1 divided by x. In this case, it would be 1 divided by 1, or if you want the other expression with a negative exponent, it was 1 raised to the power of minus 1, which is also worth 1. The second derivative was minus 1 divided by x squared, or minus x raised to the minus 2. Well, in any case, when I change the x by 1, I get minus 1, which is very simple. Minus 1 raised to anything. I always get minus 1. Let's continue with the third derivative. This one was 2 divided by x cubed, or also 2 times x raised to the power of minus 3. Changing the x by 1, I get simply 2 in this case. Now I have the values of the first derivative at 1, the second derivative at 1, and the third derivative at 1. What was the expression of the Taylor polynomial of order 3? This one. I have already substituted the function into the expression for a in the formula for 1. The Taylor polynomial of degree 3 is the function at 1 plus the first derivative at 1 times x minus 1 plus the second derivative at 1 over 2 factorial times x minus 1 squared plus the third derivative at 1 over 3 factorial times x minus 1 cubed. Now, all we have to do is substitute each of these values, 0, 1, minus 1, and 2 for these variables. What am I left with then? F of 1 is worth 0. If prime of 1 is worth 1, as you can see above, the second derivative at 1 is worth minus 1, which is why I put it up here, and the third derivative at 1 is worth 2, so I put 2 divided by 6. Why 6? Because of the 3 factorial, which is 3 times 2 times 1. That's why it's 6. I don't include the 0. Here I have 1 times x minus 1, which is x minus 1. I leave the minus 1/2 as it is, as it's easier to calculate it this way, plus 2/6, which simplifies to 1/3 times x minus 1 cubed. Now I have the Taylor polynomial of order 3. Take a moment to carefully examine the graphical representation for the provided problem. The blue function represents the natural logarithm of x, and the pink function is the polynomial of degree 3. Notice that around the point 1, these two functions are almost identical. At x equals 1, they coincide, but even in the vicinity of 1, the error is minimal. Let's put this into perspective with some numbers. The natural logarithm of 1.2 is approximately 0.18232, whereas the degree 3 polynomial we calculated earlier yields approximately 0.1826. The discrepancy between these values only occurs in the 4th decimal place. this level of accuracy provides an excellent approximation, especially for a value that might not have been known with such precision previously. It is true that you have to calculate a polynomial of degree 3, and then substitute 1.2. That's true. It's not a trivial technique. But actually, calculating a polynomial of degree 3 in 1.2 may be more or less difficult to calculate, but it can be calculated. On the other hand, calculating the logarithm of 1.2 is going to be much more complicated. A polynomial of degree 3, with a little patience, can be obtained quite easily. The error made, as you can see, is only 0.0003. It's a very small error in absolute value. Furthermore, does this method consistently yield accurate results? If the nth derivative exists, we observe a significant trend, where the limit of the function minus the polynomial of x divided by x minus raised to the power of n approaches. In other words, the error diminishes as n increases, signifying that it is indeed a reliable approximation method. It's important to be careful here. We've applied this method for x equal to 1. For values significantly distant from 1, this technique is less effective. In such cases, the polynomial and the function won't provide a sufficiently close approximation, and the error can be substantial. Before saying goodbye, I would like to briefly demonstrate how this works. I made use of a program called Mathematica to generate visualizations of the natural logarithm function in a shade of blue. Alongside it, I've displayed Taylor polynomials of increasing degrees, ranging from 1 up to 10, while I decided not to provide the actual formulas for each degree of the polynomial. The visual representations show how these polynomials approximate the function. Degree 1 offers just a linear approximation, degree 2 refines it a little bit, and degree 3 further improves the fit, as you can observe. Pay close attention to the region near the point of 0, where the approximation gets increasingly accurate. However, beyond a certain point, you'll notice a growing disparity between the polynomial and the function. As mentioned earlier, near 1, they align well, but as you move further away, especially beyond 2, the accuracy deteriorates quite considerably. The polynomial begins to decrease and approaches negative infinity, while the natural logarithm function remains relatively stable. Nevertheless, errors can accumulate and become significant. Now, let's progress through degree 5, degree 6, degree 7, degree 8, degree 9, and degree 10. From 0 to around 2, the functions closely match and the approximation is really good. But below 0 and above 2, substantial discrepancies emerge. I hope that this has been useful to you and that it will prove valuable in the future when you need to approximate various functions. Thank you very much for your attention.